Hello, am I audible?
Yes, sir.
Okay.
Yes, sir.
So today we'll start the new chapter. So that is called statistical thermodynamics. So the statistical thermodynamics is completely new for you. Statistical thermodynamics. First, we should discuss that what are the difference between the classical thermodynamics and statistical thermodynamics. Just wait, I am sharing the screen. You can see the classical thermodynamics uses the data based on the bulk properties of the matter like density, pressure, heat capacity, etc. That means in classical thermodynamics we are using the data of density, pressure, heat capacity, etc. Whereas in case of statistical thermodynamics, the statistical thermodynamics uses the molecular properties like bond length, quantized energy levels, vibrational frequencies, etc. That means the statistical thermodynamics uses from the atomic or molecular level. So generally the statistical thermodynamics deals with the microscopic properties. But for classical thermodynamics, what we have studied in the previous classes, that deals with macroscopic or bulk properties of the matter like density, pressure, temperature, heat capacity, etc. But for statistical thermodynamics, we will deal with the bond length, quantized energy levels, vibrational frequencies, and bond energies of atomic or molecular energy levels. As an example, the experimental value of enthalpy of formation of water is this. So this is the from classical thermodynamics. So the experimental value of enthalpy of formation of water is minus 241.8 kilojoule per mole at room temperature and 1 atmospheric pressure. It refers to the enthalpy change associated with the formation of 1 mole of water vapors from its constituent elements in their standard state under standard conditions. So this enthalpy of formation of water is like this, that is minus 231.8 kilojoule per mole. That means this much amount of energy will be released when the water in gaseous form or the water vapor will form from its constituent elements. The constituent elements of water is hydrogen gas and oxygen gas, and they should be in their standard state. The classically it states that it has nothing to do with the microscopic nature of the species involved or what determine the observed value. So in the classical thermodynamics like enthalpy of formation, we should not use any microscopic nature. On the other hand, the statistical thermodynamics deals with what individual atom or molecule determines the observed value. So in conclusion, we should say that the statistical thermodynamics ignores molecular complexity, that is the quantum mechanical nature of the molecules, whereas the statistical thermodynamics deals primarily with the quantum mechanical nature of atoms and molecules. So the statistical thermodynamics represent probabilistic approach to study the thermodynamic systems. So here we will, as we are as in the statistical thermodynamics, we will use microscopic levels, atomic or molecular levels. So here probabilistic approach will be used. Now coming to so for this, before going to the statistical term in details of the statistical thermodynamics, we should first acquainted with basic probability theory. So here in this part we will discuss about the basic probability theory. So we will start from very simple level. So the first one is, if an experiment can more than one outcome, then the probability refers to changes in getting a particular outcome. For example, if a coin has two faces, we know that a coin has two faces, that is one head and another one is tail. So the experiment involving tossing an unbiased coin. So if we toss one coin, the probability of getting head equals to 1 by 2. So that is the probability of getting head is 1 by 2. That is 50% chance getting a head, and similarly 50% chance getting a tail in a throw of a coin. So if you throw a coin or if you toss a coin, so there is 50% chance getting one head and another 50% chance getting tail, and hence the probability for getting the head is 1 by 2. One means two options are there, two choices are there. So for head, one choice divided by total number of choices, so that is 1 by 2. Hence the probability of getting head is 1 by 2, and similarly the probability of getting tail is also 1 by 2. Now if we count the total probability of all the events or all the outcomes in an experiment, it is always equals to 1. So the probability of getting head plus probability of getting tail, that will become 1. Now coming to the next part, that is, if two coins are tossed simultaneously, then the possible outcomes may be, the two coins may be head, first may be head, second may be tail, first may be tail, second may be head, and the two coins may be tail. So these are the possible outcomes of tossing two coins simultaneously. So the collection of all possible outcomes in an experiment is known as sample space. Again, you have to remember, so this is the definition of sample space. So the sample space means the collection of all possible outcomes in an experiment, that is known as sample space. And another a term that is called event. The event refers to any outcome or collection of outcome in the sample space, or may include the null set as well as set of all possible outcomes. For example, the sample space of tossing two coins has four events. So if we toss two coins simultaneously, so it has four events or four outcomes. Event means outcomes. The four outcomes may be H, may be tail, may be head, may be tail, head. So these are the four outcomes or four events of tossing two coins simultaneously. These constitute the sample space for the experiment. So these are the total all the possible outcomes or all the possible events are called as the sample space. Now coming to another example, let us take an example of traveling city A from city A to city C via city B. So this is another example. So here we are discussing very common examples in order to know the basic principle of statistics. So we are so let us taking an example of traveling from city A to city C via city B. If there are X ways of reaching city B to city A and Y ways of going from city B to city C, then the total number of ways one can go city A to city C will be X1. That means here you have to travel from A to C via B, and the number of ways for traveling A to B is X, the number of ways for traveling C to B is Y, and hence the total number of ways for traveling from A to C is xy. Therefore, the sample space of this event will consist of all the elements of xy elements. So the sample space consists of all possible outcomes. So the combination of all possible outcomes is called as sample space. Now coming to the next one, if the sample space has n mutually exclusive events and the event of interest A occurs I times, then the probability of that event is given as probability again I am repeating that one. If the sample space has n mutually exclusive events and an event of interest A, suppose the particular result is A which occurs I times, then the probability of getting A is equals to I divided by n. I is the possible events for occur A and n is the total number of events. So the probability of that event PA equals to I divided by n. Therefore, the probability of event getting one head and one tail is 2 by 4. Total number of events for tossing two coins are 4. Total number of events 4, and the probability of getting one head and one tail is 2 divided by 4, that is equal to half. In this case, the event is getting one head and one tail, and that includes the two elements of the sample space. It refers to the following subset HT or TH of the sample space. This example refers the probability associated with a single experiment of throwing two coins simultaneously. Now coming to an example, consider an experiment involving tossing a coin 4 times. Consider an experiment involving tossing a coin 4 times and calculate the probability of getting at least two heads in the experiment. So in this case, the table will be like this. In this case, we have a coin that is to be tossed 4 times. In every time, we have two possible outcomes, that may be one head or one tail. We can write down all the possible outcomes of experiment as follows. The outcome number one. So this is the outcome number one. You have to toss the coin 4 times. The outcome number one is like this. The four heads for toss one head, for toss two head, toss three head, for toss four head. And similarly, the second outcome will be like this: one tail, and after that three consecutive head. The third event will be like this: head, after that a tail, after that two heads. And the fourth event will be like this: two heads, tail, and then head. The fifth event will be like this: three continuous head, then tail. The sixth event will be like this: tail, tail, head, head. So so if you count the total possibility, so the total number of outcomes will be 16. Thus, there there are total 16 possible outcomes of experiment of tossing a coin 4 times. That is, the sample space has 16 outcomes. So if you toss a coin 4 times, the number of the sample space has 16 outcomes. So these are the possible 16 outcomes here mentioned in the table. Now, of the 16 possible outcomes, 11 meets our experiment, our requirement. Our requirement having at least two heads. According to the question, our requirement is we need at least two heads. So out of the 16 possible number of outcomes, 11 outcomes meet our requirement, which 11 outcomes having at least two heads. That means at least two head means there may be two heads, maybe three heads, or maybe four heads. So out of the 16 outcomes, 11 outcomes meet our requirement according to the question. So therefore, the probability to getting at least two heads after tossing a coin of 4 times will be 11 by 16. That is the number of desired outcomes divided by total number of possible outcomes. So that is the probability. And similarly, when we roll on dice, so when we roll one dice means it will have 6 faces, right? So the one which has a chance of any one of the 6 faces on the top face at the, so the probability of getting number 6 on the top face will be 1 by 2. So if you roll one dice, the probability of getting number 6 on the top face or the probability of getting 6 on the top face will be 1 by 6, as it is one of the 6 possible outcomes. Similarly, the number other numbers from 1 to 5 will be have same probability. Suppose that means if you roll one dice, the probability of getting 6 is 1 by 6. The probability of getting 5 is 1 by 6. The probability of getting 6 is 4 is 1 by 5. The probability of getting 3 is 1 by, the probability of getting 6 is 1 by 6, the probability of getting 5 is 1 by 6, the probability of getting 4 is 1 by 6, the probability of getting 3 is 1 by 6, and also the probability of getting 2 is 1 by 6 and 1 is 1 by 6. So the if you add the total number of probabilities 1 by 6, 1 by 6, 1 by 6, 6 times, so that will become 1. Now consider so these are the basic principle of probability or the basic probability theory. Before going to the statistical thermodynamics, we should know what are the basic probability theories. Now consider slightly more complex cases of rolling a pair of dice. So if you roll a pair of dice, there is only one outcome in which we will get sum of the numbers of the top faces equals to 2. That means when both the dice will show 1, such an event is identified throws of a 2. Similarly, there are only two possibilities of throws of a 3. Only one possibility of throws of 2. That is the two face will be 1 and 1. And similarly, there will be three possibilities. There will be two possibilities, that is throws of 3. And the two possibilities are the first dice will show 2, the second dice will show 1. Or the other possibility, the first dice will show 1 and the second dice will show 2. So all the possibilities of rolling a pair of dice are shown below. So here the the if the outcome will be 2, that will the number of ways will be 1. If the outcome will be 3, the number of ways will be 2. The outcome if we need the outcome as 4, the number of ways will be 3. If the outcome will be 5, the number of ways will be 4. Outcome for outcome 6, the number of ways will be 5. For outcome 7, the number of ways will be 6. For outcome 8, the number of ways will after that will decrease 5. Similarly, for outcome 9, the sample space for rolling a pair of dice has a total 36 outcomes. You may note that in the above example, throwing a 7 is the more probable event. That is, one can be accomplished the greatest number of ways. So throwing a 7, so this table, you can show, you can see throwing a 7 having the highest number of ways. Since it occurs in 6 possible ways, it has a probability of getting 7 is 6 by 36, that is 1 by 6. You may also know that 6, the first dice 2, second dice 5, this is the second way, or the third way, first 3, second 4, or the fourth way, first 4, second 3, or the fifth way, first 5, second 2, or the sixth way, first 6, second 1. And these half HT and TH are considered equivalent. It is important to state that the random and randomized variables or quantities are those variables whose value can change throughout the course of an experiment or series of events. In the above examples, the size of the coin or the number of top faces of the dice are the variables that changes the outcome of the experiment. So these variables can be discrete variables, that is ones that can have outcome, one that can have countable number of values. For example, a coin has only two sides, so it has only two variables. Whereas a dice has six variables, because a dice has six faces, so six variables are there. In the event of picking, one student for a class of 60 students has 60 variables. It is important to note that the number of outcomes may be astronomical. However, as long as possible outcomes are countable, it will remain discrete. But in case of discrete variables, the sample space is represented as a collection of all the variables. For example, sample space of experiment involving throwing a pair dice will be 1, 2, 3, 4, 5, 6. On the other hand, we can have continuous variable that can. So here we have discussed the discrete variable. Discrete variables, that means the number of variables, that means the countable number of values. So that is called a discrete variables. Now coming to the next variable, that is called continuous variable. The continuous variable that can have any values in the given range of values, say a real number between 0 to 1, an example of continuous variable. Contrasting with the discrete variable, a continuous variable has uncountable set of possible outcomes anywhere between from 0 anywhere from 0 Kelvin onwards. So yet another example could be distance traveled by a different people within a given time interval. So these are the examples of continuous variable. Now in case of continuous variable, the sample space is represented by stating a set limit in which the variables vary. The value of x maybe has the values in the range of a less than equal to x less than equal to b. For example, if the continuous variables x can have any value from 1 to 100, it will be represented as 1 less than equals to x less than equals to 100. So these are the different continuous and discrete variables. Now coming to the permutations and combinations. So here we are discussing the basic probability theory. So permutation and combination, to calculate the probability of an event, we need to count the total number of events. This is an easy exercise in situations with a small number of events. If small number of events will be there, we can easily count and calculate the probability of an event. However, if the exercise becomes increasingly difficult when the number of events will be large, if the number of events will be large, it is very difficult to count and calculate the probability of a particular event. For example, if you simultaneously toss 100 coins or roll 20 dice, then much more, so it will be difficult to count the probability in principle. Now, according to the principle, if there are n1 ways of doing the first thing, n2 ways of doing the second thing, n3 ways of doing the third thing, and so on, then the total number of possible outcomes will be n1 into n2 into n3 and so on. Now, let us calculate the total number of outcomes of rolling a pair of dice by using this fundamental counting. So here we will apply the fundamental counting principle because in thermodynamics or because in chemistry, we should deal with large numbers. Because in chemistry, 1 mole means 6.022 into 10 to the power 23 numbers. So, in generally in chemistry, we are using very large numbers. So, it is very difficult to count and to get the possible events individually. Now let us calculate the total number of outcomes of rolling a pair of dice. So when we are using very large numbers, then we should use the fundamental counting principle. So according to the fundamental counting principle, if there are N1 into N2 into N3 dot dot. Now let us consider the total number of outcomes of rolling a pair of dice by using fundamental counting principle. For rolling the first dice, there are 6 possible outcomes. Similarly, for rolling the second dice, again 6 possible outcomes. Then the total number of possible outcomes will be 6 into 6. Similarly, if you roll 3 dice, then the total number of outcomes will be 6 to the power 3. And if you roll n dice, the total number of outcomes will be 6 to the power n. It is equivalent to the number of outcomes for drawing r objects from a total n objects, such that firstly the objects are replaced, and again it is equivalent to the number of outcomes objects from a total n objects, such that firstly the objects are replaced after every pick, and secondly the order in which the objects are drawn does not matter. Is giving the so the number of objects will be n to the power r. That means the number of outcomes of drawing r objects from a total number of n objects, and here the number of permutations will be n to the power r. We'll discuss example. Now coming to the permutations. Let us now count the example 4 different balls D, and the calculate the number of possible ways of randomly selecting 4 original balls out of the box without replacement. Again, I am repeating the question. Consider a box containing 4 different balls labeled as A, B, C, and D. Calculate the number of possible ways of randomly select P. And similarly, for the third P and fourth P, we have only one possibility. Second P, 3 possibilities are there. For the third P, 2 possibilities are there. And for the fourth P, one possibility will be there. And hence, the number of ways of a total sequential but independent choice can be 4 into 3 into 2. Hello.
Yes, sir.
Hello. Okay.
Yes, sir.
Okay.
You're
So
audible, sir.
after that, we will consider the example. So these are very simple things. You should go through the permutation and combination. Easily you can understand that. So now coming to the example 3.3, calculate the number of possible unique 9-digit numbers that can be formed by using the digits 1 to 9 just once in the number. That means we have to select a 9-digit number. Using 1, 2, 3, 4, 5, 6, 7, 8, 9, and every digit that none of the digits should be repeated. While writing the desired number, there are 9 choices available for the first digit. For the first digit, we have nine, choices. Possible unique 9-digit number will be 9 into 8 into 7 into 6 into 5 into 4 into 3 into number. In the above example is made up of unique
Hello? Hello?
Yes, hello. I think so. Sir has left the meeting, right?
Yes.
Okay, so from which portion? Okay, I am sharing the screen, and you will tell that from which portion the net was disconnected. All of you, I have discussed these things. Hello? Hello?
Hello, sir.
Yes,
Okay, so
sir.
now is it visible?
Yes, sir.
Okay,
Yes, sir.
so
Yes, sir.
you can see. So this is the summary of the discussion. So the expression, so the table is like this. The expression of for number of possible outcomes for picking R object out of a total of n object under different conditions. That means you have to select R object from a total of n objects. And if no replacement will be there, and ordered arrangement is necessary. Ordered arrangement means you have to select which one will come first and which one will come second. So that is one condition will be there. If ordered arrangement is necessary, then the expression for picking R object out of a total n object will be NPR, that is the permutation NPR, so that the formula will be n factorial divided by n minus R factorial. If no replacement will be there and ordered arrangement is not necessary, that means no ordered arrangement, then you should go through NCR. So NCR equals to n factorial divided by R factorial into n minus R factorial. And if replacement is allowed and it required ordered arrangement, so the total number of ways of picking up R object out of a n object will be n to the power R. And if replacement is allowed and no ordered arrangement will be there, then the total number of picking up R object out of a total n object will be n minus R minus 1 factorial divided by R factorial into n minus 1 factorial. So now coming to, we have considered, so these are the summary what we have discussed in the probability theory. We have so far considered the situation of picking a certain number of objects, giving a total number, picking the object with or without restriction. So now we'll move to the second probability part. So here with or without so restriction. Distributing object with restriction and a distributing object without restriction. Now let three identical boxes. Consider the distribution of a red color ball among them. Again, let us three identical boxes are there. So these are the three identical boxes. And within the three identical boxes, we have to distribute red color ball among them. We know that it can be accomplished through three different ways. That is in the figure number 1A, you can see. So that can be accomplished in three different ways. Three different ways means if we take two identical red ball, three different ways, that is the ball either in first or in second or in third box. The ball either in first or in second or in third box. Right?
Sir, again you are not visible
Okay.
and not audible. I'm
Okay,
sorry.
okay. So let us take three identical boxes and consider the distribution of a red color ball, distribution of a red colored ball. Okay, just I and stay here. Okay, so now we will continue the section. So here you can see. Let us take three identical boxes. All the three boxes will be identical. That means same. And consider the distribution of a red color ball among them. We know that it can be accomplished in three different ways. That means the red ball can be placed in first box, or the red ball can be placed in second box, or the red ball can be placed in third box. So that can be accomplished in three different ways. That is, the ball is in either first or second or third box. Now, if we take two identical red balls and try to distribute them into the three identical boxes, with the condition that each box can have only one ball. Each box can have only one ball. We find again there are three possibilities as shown. The two balls can be placed in first and third box. This is the first possibility. The two balls will be placed in first and second box. Second possibility. The two balls can be placed in second and third box. Second and third boxes. So this is the third possibility. However, if we take a red and a blue ball, so now we are going to gradually we are going to some complexity. If we take a red and a blue ball, the balls are distinguishable now. Two balls, one is red and another one is blue ball. So now the balls are distinguishable and distribute among the three boxes. Again, the condition that each box can have only one ball. That means you cannot put two balls in a single box. We find now there are six possible ways. So the red ball can be placed. So this is the first way, where the red ball can be placed in first and blue in second. The second possible way, red in first, blue in third. The third possibility, blue first, red second. The fourth possibility, red second, blue third. The fifth possibility, blue first, red third. The sixth possibility, blue second, red third. So these are the six possible ways we can distribute two distinguishable balls. Distinguishable ball means two different color balls among the three identical boxes. We can say that when the distinguishable objects are distributed in two separate subsystems, there are more possible ways of doing so can be as compared to indistinguishable objects. So here we have placed two balls, two identical balls in three boxes. The number of probability was 3. But when we will put two distinguishable balls in three boxes, the number of probability will become 6. Now coming to one question, calculate the number of ways in which the three balls of different color can be distributed among four identical boxes without any restriction. Again, calculate the number of ways in which three balls of different colors can be distributed among four identical boxes without any restriction. And the second part of this question, calculate the number of ways if we put a condition that box 1 can have only one ball, box 2 can have two balls, whereas the third and fourth boxes have no balls at all. So let us see the solution. Let us label the balls as red ball. We have three balls of different color. So the three balls are red, blue, and green balls. And the ball R can be placed in any of the four boxes for each of these. The ball B can also be placed in any of the four boxes. Thus, there are 4 into 4, that is 16 ways of placing R and B balls. And again, for each of these, there are 4 ways of placing the ball G. So the total number of ways equals to 4 into 4 into 4, that is 64. And coming to the second question, under the condition that given restriction, the number of ways reduced to 3. So here in the second question, one restriction was there. Calculate the number of ways you will put a condition that the box 1 can have only one ball and box 2 can have two balls. So it will reduce to 3 probabilities. So in general, the total n distinguishable objects, distinguishable means different objects. N different objects are distributed in k boxes in such a way that n1, n2, n3 and nk objects respectively. Then according to the combinatorial mathematics, the number of ways W is given as W equals to n factorial divided by n1 factorial into n2 factorial into n3 factorial into nk factorial. So in the present case, n equals to 3, n1 equals to 1, n2 equals to 2, n3 equals to 0, n4 equals to 0. So according to the second question, so this is the formula. So W equals to 3 factorial divided by 1 factorial into 2 factorial into 0 factorial into 0 factorial. And you should know that 0 factorial is 1. So that is equals to 3. Now coming to the Stirling approximation, you can see one question is there in the last semester examination. That question is from the Stirling approximation. I have already sent the question. You can see the question. Question number I have already sent. You can see the question number. One question was there. Question number 2D. So that was a 3 marks question. Using Stirling's approximation, calculate the percentage of error introduced in computing the values of 6 factorial. So here we will go for the Stirling's approximation, derivation of Stirling's approximation. So it is easier to calculate the factorial of small numbers as used in the example above. So whatever we have discussed, so that based upon small numbers, so that was easy to calculate the factorials. However, in chemistry, we will deal with a very large numbers, for example 10 to the power 22, whose factorial are beyond the range of the most computing devices. So you may have noticed the common handy scientific calculator out of the range when even for 70 factorial. So as a result greater than 10 to the power 100, the limit of the calculator. In such cases, we have to use Stirling approximation. So in many scientific calculator, if if you calculate more than 70 factorial, it will say out of range. Or similarly, if you want to find the calculation of 10 to the power 100, that will also show out of range. So for a large number of samples, we have to use this Stirling's approximation, because in chemistry we will deal with very large number of atoms or molecules. Suppose 1 mole of atom means that is Avogadro's number, that is 6.022 into 10 to the power 23. So to calculate such a large number, we can use an expression that is called Stirling's approximation to calculate the factorial. And we know that the factorial number n factorial is defined as n into n minus 1 into n minus 2 into n minus 3 dot 3 into 2 into 1. So that we know that is n factorial. Now taking natural logarithm of the above expression both sides, so the equation 3.12 will become, so if we take logarithm of the above expression both sides, the expression will become ln n factorial equals to ln n into n minus 1 into n minus 2 into n minus 3 dot 3 2 1, this one. That means we have only taken natural logarithm of both sides of equation 3.12. So that is equals to, the right hand side will become ln n, because we know that ln a into ln b equals ln a into b equals to ln a plus ln b. So the right hand side of the above equation will become ln n plus ln n minus 1 plus ln n minus 2 plus ln n minus 3 dot dot plus ln 3 plus ln 2 plus ln 1. We can write the expression as the summation of terms at the right hand side, that is ln n factorial equals to summation of ln n, where the value of n ranges from 1 to n. Since n is a very large, the summation can be replaced by integrating with the limits. Therefore, we can write ln n factorial equals to integration of ln n dn from 1 to n, and here the limit is 1 to n. The lowest number is 1 and the highest number is n. So which is equals to n ln n minus n with limit 1 to n. Now which is equals to n ln n minus n ln n minus n minus 1 ln 1 ln 1 minus 1. So that is equals to n ln n minus n. Neglecting this small number, we can write n ln n minus n. Then according to the Stirling's approximation, ln n factorial equals to ln n factorial equals to n ln n minus n. So this is Stirling's approximation. So you may note that in the Stirling's approximation, the fact approximates ln n factorial and not n factorial. The factorial is a product of number where ln n factorial is the sum, which is easier to work with. The actual and approximated value of ln n factorial for the different values of n are given below. Suppose the value of n is 5, then the ln n factorial equals to 4.79, and according to Stirling approximation, we know that, so this is the Stirling's approximation. This one you can see ln n factorial equals to n ln n minus n. So if the number is 5, then the RHS of the Stirling's approximation will become 4.79, and the LHS, if the number is 5, the LHS of the Stirling's approximation will become 4.79, and the RHS of the Stirling's approximation will become 3.47. That means the percentage error is 27.56. Now, if the number is 10, the percentage error will be 13.71. If the number is 100, the percentage error will be 0.89. That means if the number of objects will increase, the percentage of error in the Stirling approximation will gradually decrease. If the number is 1000, then the percentage of error is 0.07. And if the number is 1 lakh, the percentage of error is 0.00061, which is negligible. That means the Stirling's approximation will give good results for very large values of n. However, for smaller values of n, the result does not match the actual value. So if very large numbers are there, then Stirling's approximation hold good results for a very large values of n. But if for smaller values of n that does not match the actual value, percentage of error will be there. Now, here the question is, calculate the percentage of error introduced in computing the values of 50 factorial using Stirling's approximation. And you can see the previous, the last semester question number 2D. You can see, using Stirling's approximation, calculate the percentage of error introduced in computing the values of 6 factorial. So here, if we apply the values for 6 factorial, the Stirling's approximation is ln 6 factorial equals to 6 ln 6 minus 6. And using this expression, you can easily calculate the percentage of error, and you should take scientific calculator to your to the examination, and using that scientific calculation you can easily calculate the question number 2D. Now coming to the next part, the probability distribution functions. So when an experiment is carried out, the different possible outcomes, and each outcome has some probability of occurrence. To characterize a random variable, we first need the formation of all the possible outcomes of the elementary events of the random variables, and then getting the probability and getting the value of the possible outcomes. Recall that in the case of tossing a coin twice, there are 4 possible outcomes. So if you toss a coin twice, there will be 4 possible outcomes. We could calculate the probability of getting particular outcome. The probability of distribution refers to the variation of probability of occurrence of all the possible outcomes in an experiment. Now let us recall the experiment given above, in which already we have discussed that experiment. 2 dice are rolled simultaneously, and the minimum value of sum of the number on the top faces of the 2 dice is 1 plus 1, that is 2, and the maximum value is that is 6 plus 6, that is 12. And the other possibilities are the summation. The other possible summations are 3, 4, 5, 6, 7, 8, 9, 10, and 11. So the minimum summation value will be 2, and the maximum summation value will be 12, and the other summation values are 3, 4, 5, 6, 7, 8, 9, 10, and 11. So the number of permutations and probabilities of different outcomes of rolling 2 dice, for getting summation 2, the permutations are 1 and 1, and the number of permutation is 1. The total and hence the probability is 1 by 36, that is 0.028. For getting a summation of 3, there will be 2 permutations. Either the first dice will be 2, second dice will be 1, or the first dice will be 1, second dice will be 2. And the number of permutations will be 2, and the probability will be 2 by 36. Similarly, for the highest probability we can observe for 7. For 7, the number of permutations will be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. And the number of permutations are 6. Here these are the permutations, and the number of permutations are 6, 1, 2, 3, 4, 5, 6 permutations are there, and hence the probability is 6 by 36, which is the highest probability. Now, in the case of possible outcomes of 2 dice, for 2 dice are 6 each, are independent of each other, then according to the fundamental counting principle, the total number of possible outcomes, that is the number of permutations, equals to 36. The last column of the table gives the probability of each possible permutations of sum of the number on the top faces of the two dice. You can clearly see the probability depends upon the outcome. A plot of the probability against the outcome is known as probability distribution curve. So if you draw a graph, so that is called probability distribution curve, and the probability distribution curve will be like this. This is for the number 7, summation 7, so that will be the highest probability. Yes, so this is the figure you can see for 7, that is the highest probability. So now, so these are the questions. You should go through these questions. So that means in the first part, we have only discussed the permutation or combination or the normal general probability theories. What we have studied in our mathematics that is general probability theory. And after that, we will move to the statistical thermodynamics part. So in the statistical thermodynamics part, the first one is Boltzmann's distribution. So in a system containing many molecules, the variable quantized energy states are occupied by different fraction of molecules. So suppose in a system large number of molecules are there, and the available quantized energy states are occupied by different fractions of molecules. So in molecule, we know that in a particular molecule, different quantized energy levels are there. Just like in a single atom, different quantized energy levels are there. For atom, the energy levels are K, L, first cell, second cell, third cell, etc. And similarly, for the molecule, different quantized energy states are there, and the quantized energy states are occupied by different fraction of molecules. Out of the total number of molecules, different fractions of molecules are present at different quantized energy levels. So this is entire population of the molecule is distributed among the different energy states. Alternatively, we can say that the total energy of the system is distributed among the constituent molecules. Now, Boltzmann was the first person to propose an expression to calculate the population of different energy levels. Population of different energy levels means the number of molecules present in different energy levels. Here, population means population of a particular energy level means the number of molecules present in that particular energy level, that is known as population. The expression is known as Boltzmann distribution function, and essentially a probability distribution function that allows to calculate the probability of finding the system in a certain energy state. Now coming to microstates and configurations. Let us take a simple molecular system consisting of 3 quantum particles. So here we will consider a simple molecular system having 3 quantum particles that are collectively have an energy equals to say 3 quanta. The energy states available for the particle with energy levels, again I am repeating that one. Let us take a simple molecular system consisting of 3 quantum of particles. So in a molecular system, 3 quantum of particles are there that collectively have an energy equals to 3 quanta. So the energy states available for the particle have energies 0, epsilon 0, 2 epsilon 0, 3 epsilon 0. So for the first state, the energy is 0. For the second state, the energy is epsilon 0. For the third state, that is 2 epsilon 0. For the fourth state, that is 3 epsilon 0, and so on. Here, epsilon 0 represents a quantum of energy. Now, what is the most probable distribution of energy? So the question will arise, what is the most probable distribution of energy, and what is the most likely way in which the total energy 3 quanta is distributed among the particle of the system? That means the total energy of the system should be 3 quanta, that is should be 3 epsilon 0, and we have to place 3 molecules in different energy levels. So the first possible is that if we put 3 molecules at the energy level epsilon, then the total energy of the system will become 3 epsilon or 3 quanta. Similarly, in the second case, if we put one molecule at 0 energy level, one at epsilon energy level, and one at 2 epsilon energy level, the total energy of the system will become 3 epsilon 0 or 3 quanta. And another probability is there. If we put 2 molecules at 0 energy level and one molecule at 3 epsilon energy level, then the total energy of the system will also become 3 epsilon 0. Thus, we see in the above example, there are 3 different ways of arranging 3 particles or 3 molecules in various energy states such that the total energy of the system will become 3 quanta, that is 3 epsilon 0. Such arrangement of the molecule in different energy states are called configurations. So here one question is there. consider a system consisting of 5 indistinguishable particles. That means 5 different particles will be there. So here n equals to 5, which can occupy any of the available energy levels having energy equals to epsilon 0, 2 epsilon 0, 3 epsilon 0, 4 epsilon 0, 5 epsilon 0. If total energy of the system is 10 epsilon 0, identify the different possible ways in which the molecules can occupy in various energy states. Now coming to the figure. So the first possible is that all the 5 molecules will present at 2 epsilon 0. So the total energy will become 10 epsilon 0. For second possibility, one molecule will present at epsilon 0, 3 molecules will present at 2 epsilon 0, and one molecule will present at 3 epsilon 0. So the total energy of the system will become 10 epsilon 0. Similarly, for the third probability, 2 molecules will present at epsilon 0 energy level, another 2 molecules will present at 2 epsilon 0 energy level, and the last molecule will present at 4 epsilon 0 energy level. You can see in the third probability, the total energy will also become 10 epsilon 0. And this is the fourth probability, and this is the fifth, and this is the sixth. So these are the 6 different ways of arranging the molecules in different energy levels, so that the total energy level of the system will become 10 epsilon 0. Now let us see what happens if the molecules are distinguishable. So when the distinguishable objects are distributed into the separate subsystems, there are more possible ways of doing so as compared to that of the indistinguishable object. In the previous case, we have discussed the 5 molecules are indistinguishable. That means the 5 molecules are equivalent. But here in the second case, we'll discuss the 5 molecules are different. So if the 5 molecules are different, then the number of possible ways of arrangement will more. Let us consider the example of distribution of 3 quanta energy among the 3 quantum particles are discussed above. Now we will take these particles to be indistinguishable. So here we have discussed 3 identical particles will arrange in 4 different energy levels, so that the total energy of the system will become 3 epsilon 0. So here, as the 3 molecules are distinguishable, here we have observed that the total number of arrangement will be 3. So here the total number of arrangement will be 3. Here all the 3 molecules are equivalent or indistinguishable. But here in the second case, if the 3 molecules are indistinguishable, that is red, green and blue, right? We have mentioned the 3 molecules to be red, green and blue, and the total energy of the system to be 3 epsilon 0. So the first configuration is like this. This is the first microstate, where all the 3 red, green and blue balls will be placed in first energy level, that is will be placed in epsilon 0 energy level, and hence the total energy of the system will become 3 epsilon 0. And for configuration 2, so for configuration 1 microstate will be there, because all the 3 molecules are placed in the same energy level epsilon 0, and hence the total energy of the system will become 3 epsilon 0. And for configuration 2, we have 6 microstates. So here the red will be placed in 0 energy level, the green will be placed in epsilon 0 energy level, the blue will be placed in 2 epsilon 0 energy level. So this is the first microstate, where the total energy will become 3 epsilon 0. Similarly, for the second microstate, the red will be placed in 0 energy level. Just exchange this one. The blue will be placed in epsilon energy level. The green will be placed in 2 epsilon 0 energy level. So total energy will become 3 epsilon 0. And for the third microstates, 0 will be placed in green will be placed in 0 energy level, red will be placed in epsilon 0 energy level, blue will be placed in 2 epsilon 0 energy level. So the total energy will become 3 epsilon 0. For the fourth microstates, green will placed in 0 energy level, just exchange. This will exchange. Green will placed in 0 energy level, blue will placed in epsilon 0 energy level, and red will placed in 2 epsilon 0 energy level. For the fifth microstate, blue will placed in 0 energy level, red will placed in epsilon 0 energy level, and green will placed in 2 epsilon 0 energy level. And for the sixth microstate, these two will exchange. So here for configuration T2 we will get the 6 microstates like this. So why 6 microstates are coming in configuration 2? Because all the 3 balls are different or distinguishable. But in case of the above example, when the 3 balls was identical, only one microstate was there. But as the 3 balls are not identical, here for configuration 2, we are getting 6 microstates. Now similarly, when the 3 balls are equivalent or indistinguishable, for configuration 3, we will get 1 microstate, whereas when the 3 balls will be different or distinguishable, for configuration 3, we will get 3 microstates. So a configuration in this case can be represented as N0, N1, N2, N3, where N0, N1, N2, N3 refers to the number of particles in the energy state 0, epsilon 0, 2 epsilon 0, 3 epsilon 0 respectively. So three configurations give the above will be represented as 0, 3, 0, 0. So here the total energy will become 3 epsilon 0. The second configuration is 1, 1, 1, 0. The total energy will become 3 epsilon 0. The third configuration is 2, 0, 0, 1 respectively. It is important to note that the total energy of all the arrangement is the same. That is only difference is distribution of the energy over the particles. So the total number of microstates associated with a given configuration is known as weight of the configuration and is represented by W. Here weight means the total number of microstates present in a particular configuration. That is called weight. So that is represented as W. Now a question comes that which of the possible configuration is likely to be observed for the system at equilibrium? Since all the microstates have an equal probability of being observed, the probability of observing 1, 1, 1, 0 configuration will be the maximum number of microstates, so that is 6 microstates. So the number of microstates in a configuration, that is called W. So for the configuration 1, 1, 1, 0, that will show the maximum number of microstates, so that is W equals to 6. So that here we have discussed, so here W equals to 6. So the probability of observing this configuration is simply the microstates associated with this configuration divided by total number of microstates possible. So the total number of microstates is 6 plus 1 7 plus 3 10. So total number of microstates is 10, and the possibility of getting this configuration 1, 1, 1, 0, so that is 6 by 10, that is 0.6. So here one question is that what is the relationship between microstates and configuration? So you can easily solve all these things if you will go through the what we have discussed today. So these are very easy things. So another example is there. Consider a system consisting of 5 molecules. So here 5 molecules will be there which can occupy any of the available energy states having energies. So 5 molecules are there and the energies levels having energy equals to 0, epsilon, 2 epsilon, 3 epsilon, 4 epsilon, 5 epsilon. So among the 6 energy levels, we have to put 5 molecules. If the total energy of the system will and so that the total energy of the system should be 5 epsilon 0. Now calculate the possible ways in which the molecule can occupy the various energy levels. Repeat this exercise with 50, 500 and 1000 molecules can be distributed among the same energy level with a total energy of the system become 5 epsilon. Comment the result. So here we will solve the bit A. The possible distribution of the corresponding weights of the probability of 5 molecules under given set of condition is there. So here the distribution or configuration. So this is the first distribution. So here in the first distribution, we have to put 4 molecules at 0 energy level and 1 molecule at 5 epsilon 0 energy level. So the total energy of the system will become 5 epsilon 0. Here W equals to 5 and hence probability equals to W by W total, that is equal to 0.04. Similarly, for the second configuration, we will put 3 molecules at 0 energy level. So here N1 means 0 energy level, N0 means 0 energy level, N1 means epsilon energy level, N2 means 2 epsilon energy level, N3 means 3 epsilon 0, N4 means 4 epsilon 0, N4, N5 means 5 epsilon 0. So in the second case, you will put 3 molecules at 0 energy level, 1 molecule at epsilon energy level, and 1 molecule at 4 epsilon 0 energy, 4 epsilon energy level. So the total energy will become 5 epsilon. And here W equals to 20 and the probability will be 0.16. Similarly, you will find highest probability is there 0.24 and 0.24. When you will put 2 molecules at 0 energy level, 2 molecules at epsilon energy level, and 1 molecule at 3 epsilon energy level. That is, the probability will be 0.24. And if you see, the total probability will become 1 and the total number of microstates, that is W, equals to 125. Now in the second bit, repeat the exercise with 50 molecules, 500 molecules and 1000 molecules so that the total energy will become 5 epsilon 0. So for 50 molecules, to arrangement 50 molecules in these 6 energy levels, and so that the total energy of the system will become 5 epsilon 0, the first distribution is like this. We have to put 49 molecules in 0 energy level and 1 molecule in 5 epsilon energy level. So the total energy will become 5 epsilon. And here the probability is 0 probability because W equals to 50. And the second case, 48 molecules in 0 energy level, 1 molecule in epsilon energy level, 1 molecule in 4 epsilon energy level. So the total energy will become 5 epsilon. And here W equals to 2450. Here the probability is also 0. Now, so when we will put 45 molecules in 0 energy level, 5 molecules in epsilon energy level, so the total will become 5 epsilon, and here W equals to a very large number. So here we are getting the probability 0.67. And if we add the total probability, that will become 1. And similarly, for 500 molecules, so the number of microstates will increase. And similarly, for 1000 molecules, so this is the number of microstates. Now coming to derivation of Boltzmann distribution. So this thing we will discuss in the next class. Okay? Hello? So this is an important long question. So that we'll discuss in the next class.
Okay, sir.
Next class,
Okay.
sir.
So next class, I'll take next class tomorrow. Okay?
Okay, sir. Thank you, sir.